to the Quantum Feedback Loop. I'm your host, James Myers, and I also publish the Quantum Record. In this discussion, I was fascinated to learn from astronomer Lindsay House about the hunt for evidence of dark energy that will take citizen scientists over 9 billion years back into the history of the universe. What will we find out about the mysterious force that seems to be causing the accelerating expansion of the universe? I found Lindsay's analogies incredibly helpful in a discussion that I hope will intrigue you as much as it did me. Well, welcome, Lindsay House, to the Quantum Feedback Podcast. It's great to have you here and looking forward to chatting about your background and your exciting citizen science project.
Thanks, James. Excited to be here.
Well, that's great. Could you start us off maybe by just telling us a little bit about your current research and what got you to this point and what new things you're discovering in the process?
Yeah, so my background is in math and physics, and I actually took a little bit of time off before coming to grad school where I was teaching and working at a planetarium, and that was really what sparked my interest in coming back to school for astronomy. But my current research at UT Austin is a part of the Hobby Everly Telescope Dark Energy Experiment at McDonald Observatory. And I run an online citizen science project that gets the public involved for classifying some of the galaxies that we collect from the telescope. And then I, in turn, use those labels or classifications that we get from the public for machine learning.
Interesting. And how many people are involved in the project and what kind of contributions have they made to the machine learning process so far?
Yeah, we have about 14,000 volunteers in over 85 countries all around the world. So it's been really awesome to see the public be involved, and they've done an awesome job. They're doing pretty much as good as we are as the scientists at classifying these different astronomical objects. And so, yeah, we mainly have them distinguish between galaxies or stars and meteors and other objects, or we have them distinguish between galaxies and false positives or things that can go wrong with our telescope since it is such a large experiment.
Are these people from all ages as well?
Yeah, mostly all ages. I think Zooniverse as a host platform has an age limit of maybe 13. Yeah, and so mainly all ages, but I mainly advertise to high school, undergrad, but I still do it.
Well, that's neat. I'm actually going to join as well, so I'll be one of your participants in this, and I'm looking forward to that. What are some of the interesting things that the citizen scientists have found so far that weren't expected? And I'm wondering too what the advantage of having citizen scientists participate in a project like this is compared to just letting the machine go out and find what it will. Like what's the human advantage of this?
Yeah, so our project, HeadDex, is so large, really, that we were having trouble with machine learning and AI efforts in the beginning. It wasn't doing a great job, and it wasn't making it as accurate as we wanted for the dark energy science that we wanted to be able to do. And we really found that the human's eye ability for pattern recognition was really unmatched in the beginning, especially at looking at these really low signal to noise objects or these really far away galaxies. And so we use citizen science, and it's worked really well for us, and that we can do this a whole lot more efficiently, and we can get them also involved and hopefully the public in learning something as well.
Interesting. And then are you using the results from the human participants to tweak or change the way the machine learning approach is used or applied?
Yeah, it's kind of an iterative process. So we get the labels from the public, we then use machine learning, and it's kind of that unique combination right now of the machine learning and the visual classifications from the public that's yielding our best results. We can then kind of iterate on that and then put more of those sources back into Dark Energy Explorers and have the public look at another subset and then kind of do the same thing over and over again.
Wow, so it's a continuous process. The machine learning, I guess, inputs just continue to change over time, I guess, from the human participants.
Yeah, exactly.
Fascinating. And I guess, we live in this world of and time of big data where, a lot of data is fed into machines and humans across the planet are providing labels, I guess, essentially to train the machines on the content of the data. It's an interesting thing. And we're really interested in exploring citizen science because I think this is a way of kind of maybe democratizing the whole approach to data labeling in a way that really makes it accessible to the public, but also contributes something very important. I guess the participants have no particular background in the science, right, for the most part, but they're contributing something valuable and something that perhaps, I don't know whether it could be used in other machine learning models, but it sounds like it's really valuable, certainly for astronomy.
Yeah, it's been really valuable for us, and we don't require any science background. We try to make it as easy as possible, really reducing that barrier to entry so anyone can join. And yeah, they are really a part of this dark energy experiment. A lot of the sources that we're putting in, we don't have the time to look at these millions of sources. So a lot of times they're the first people to ever look at these sources. And so it's really cool. And hopefully we're doing a good job of communicating that to them, educating them, and realizing that they really are a part of this project.
It'd be exciting to be able to look at a screen and make a discovery that nobody else had seen. So, as I said, I'm very interested in participating, so I will experience that firsthand. On your website, you display this history and passion that you have for engaging the public in science. Where does that come from, and what kind of approach do you think is the most effective for engaging the public versus how science in general has approached things? I mean, I guess as an amateur in science myself, I'm not trained in science. It's something that I've kind of taught myself by following people of interest and doing my own research. But I find it, I guess sometimes it gets very technical. And how do you bring it down to a level where it's accessible and relatable to everybody?
Yeah, that's a great question. I mean, I think with astronomy, at least for me personally, I think it's this really unique science that can provide you with a different perspective on life. You're forced to kind of fight with these large cosmic scales and these, questions that are still left unknown that I think a lot of fields don't have still. And so I think forcing us to really push those boundaries of, making us uncomfortable, I think is really beautiful and can be really special and can also resonate to a lot of the issues and things that we deal with here, on Earth at the same time or with our daily life. So I think for me, that's what made me want to push through the math equation or push through the physics because it has this, bigger picture that makes it worth it. But yeah, and I think that everyone deserves to have that perspective and to at least be taught it and to make the choice whether they want to be okay with the uncomfortable.
Yeah, and I guess discovering new things and discovering new frontiers to knowledge, I guess, is always it's always important to open up paths that maybe people hadn't thought of before. And it's great to see that organizations like NASA and I guess this is primarily a NASA project that you're working on.
So we're funded by both the NSF, the National Science Foundation, as well as NASA.
Okay. And it's great to see that those organizations recognize the value of citizen participation. Is it a question of recognizing first principles in things that maybe is what really draws people to science? Is there sort of first principles of things that really just connect with people without having to do a lot of that detailed explanation?
Yeah. Maybe. I mean, I can't speak. I mean, I know my draw to science, I feel like started at even younger age of going to science museums or, doing fun like science fairs and things like that. Or I grew up in a pretty rural area in Western North Carolina where I had a beautiful view of the night sky. I think that really is what got me into science, honestly. So I think, yeah, even earlier than that, personally.
Yeah, interesting. It's like that timeless wonder that just, starts at the earliest age and continues throughout life. So that's great to be able to instill a passion for that in other people as well. So um, let's talk about the project, the Dark Energy Explorers project. If you could maybe just tell us a little bit about what the process would be. So, for example, if I want to participate, What do I do? What do I see? Do I have to participate on a regular basis? What kind of input do I provide? And then what kind of feedback do I get?
So if you want to be a dark energy explorer, you can go online to zooniverse.org, or you can download the Zooniverse app on iPhone or Android. And going to the projects, we're under physics or space projects and choosing dark energy explorers. We do ask that you make an account because that is what saves the classifications, but it's free. Anyone can participate as long as you have internet access. And once you get to Dark Energy Explorers, our current workflow is called fishing for signal in a sea of noise. So you're looking for these real galaxies that we're collecting from our experiment. And you're going to see what is called a spectra. And so you're going to see that light that's traveling, 9 to 11 billion light years away, that's traveled all the way to us, that we've captured on our Hobby Eberly telescope. And we put that in there, and we teach you basically how to classify those real galaxies and then determine what might not be a real galaxy as well, because we want to get those out of our subject sets. And so, yeah, that's essentially what you're looking at as a participant.
Okay. And so I look at these, I guess it's kind of like pixels of light on the screen, right? And I'm looking
Yeah.
for, is it motion that I'm looking for?
It's really just you're looking for the light that we've collected. So we want to make sure that we're seeing the light to know that that's from an actual object.
It's collections of light, I guess, that would make up a galaxy. So I'm looking for collections of, okay, interesting. And then, so I provide the classifications, I guess, and then is there feedback? What happens afterwards? Say I participate for a week or two, or I go on once a week or whatever. Do I learn anything from it? How does that work?
Yeah, you can participate whenever you want. Come and go as you please. So we don't have any direct feedback within Zooniverse because that would kind of defeat the purpose of citizen science. That would mean that we had someone already looking at these things to label to give you the feedback, right? But we do try and let our participants know what we are doing with their classifications. So I have published papers. We've also held some Zoom night for our participants, and we'll get together all over Zoom and talk through some different sources and classify together. We also did a virtual tour of the actual telescope. So we got to take them into the mirror coding room and talk to the actual scientists on staff. And we have all of that on our YouTube channel if people are interested in watching that. But yeah, if you sign up and make an account, that adds you to our email list. So you will be invited to those type of events if you want to be involved.
That's great. That sounds like a lot of fun, actually, to be able to meet other people too and share those experiences. How long do you think the project will go on for then?
Yeah, I'm hoping it will definitely go on at least for a couple more years, the duration of my PhD, which will be about 2 or 3 more years. But we have so much data. Like you mentioned, we're in this era of big data and especially big data astronomy with these huge surveys and just looking deeper and deeper out into space. So we could probably go on for a few more years at least.
Well, have there been any interesting citizen scientist discoveries to date? Any real moments where it's, well, we never expected that?
Yeah, I mean, like I said, the human's eye's ability for pattern recognition has been really awesome, and that we never expected them to be so accurate as they are. They have done an excellent job at cleaning out our sample, and that's essentially what we're using it for right now, is to get all the bad stuff out. We aren't using it to necessarily confirm any sources, if that makes sense. So on the positive side, so we haven't had any specific discoveries like that.
Okay. Yeah. Well, that's good. But I mean, clearly a valuable contribution in terms of making the data clear and making the data relevant, I guess, is that's essential.
Very much so, yeah.
Yeah. So you're looking for dark energy, but you're looking at signs of a physical universe. So the dark energy not being physical, but you're looking at physical evidence. So if you could just tell us a little bit about dark energy and how it relates to dark matter, which is the other thing that we hear about. I mean, what I commonly hear is that the visible physical universe is only 5% of the entire universe. And then I hear that dark energy and dark matter comprise the other 95%, the invisible universe. So by looking at the physical universe, the galaxies and those things that comprise the 5%, what can you learn about the 95%?
Yeah, great questions. So I'll start. I think the first one is the difference between dark energy and dark matter. I like to think of those two. We give them their name, dark energy and dark matter. First off, we don't know what they are, right? That's the whole problem. Probably one of the biggest unanswered mysteries of our scientific time. I like to think that they get their name dark because we can't directly observe them, right? We're really just inferring, like you said, that there is something there that is causing this effect from the actual visible matter that we can see and observe with our telescopes. And so dark matter gets its name because it kind of acts like the visible matter that we see in a gravitational way. And so we can predict and infer that it's there by understanding what we know already about gravity and actual matter. And so dark energy is a little bit different in that it acts almost like a force of energy. And so the main thing that dark energy is doing and that we discovered is that our universe is expanding. And not only is it expanding, it's expanding at an accelerating rate. So it's getting faster and faster as it moves out away from us. And I like to think about the fact that, like, if I had a ball in my hand and I threw it up, right, it would come back down here on Earth because we understand how gravity works. But if that ball was the universe and I threw it up and then that ball left my hand, and that was the Big Bang happening in the universe, starting time, right? What's happening with dark energy right now at the current phase of our universe is that ball would continue to fly through the ceiling and it would fly away from me faster and faster, and I would never be able to catch it, right? And so that's kind of how I like to think about dark energy and how it's affecting our universe. And then the second point that you said was how is that connecting to what we're doing with dark energy explorers and these galaxies that we're looking at? So essentially what we are trying to do with HET-DEX, which is the Hobby Eberly Telescope Dark Energy Experiment, is we're essentially trying to create a map of the universe. And we want to compare how these galaxies look like at a certain time period, which is about 9 to 11 billion light years away. And then we want to compare them to what the universe looks like now. And I just said that the universe is expanding at an accelerating rate. So we can kind of map the structure of what these galaxies look like at different time periods within the universe. And then we can see how they've moved and how that structure of the universe has changed over a certain period of time. And then from there, we can kind of infer how dark energy has changed or how the universe has changed and accelerated and expanded over a certain amount of time.
Yeah, that's really helpful, actually. That ball analogy, and as you were explaining how that expansion happens over time, I was just thinking, if I threw up a ball, well, it's the Earth's gravity that's dragging it down. But if I were to throw up that ball in outer space, there's nothing to stop it, right? It just goes on forever and it accelerates. I think that was the discovery, in 1998 or something like that the expansion was accelerating. Yeah, very interesting to think. So you're looking back 9 to 11 billion years, which is, I guess, getting reasonably close to the beginning of the universe, right? I mean, what the universe is thought to be 13.8 billion years old or something like that. What's the particular interest of that 9 to 11 billion year window or ring or, whatever phase of the universe? Is there a particular reason for that?
Well, we would love to go back to the very beginning, but that is kind of the basis of our survey. So we kind of fit into larger, there's other dark energy experiment surveys that are happening around the world in different universities and collaborations, but we are one of the farthest back. So there's quite a few that are observing or comparing between now and the earlier universe, objects that are closer to us. And we are sitting quite farther back in time, as I like to say, but those farther objects within our universe or our earlier universe. So kind of fitting into this larger picture of the dark energy surveys and all of us together trying to understand what dark energy is. And that's kind of where the benefit of at least our experiment sits.
Neat. Okay, so there's different groups looking at different slices of time, I guess, is what you're saying. And then by putting it all together, you can see the changes over specific times, or at least infer, hopefully, the changes. That's really interesting, actually, to think about. So maybe dark matter isn't that relevant to this, but I guess, or maybe it is, but just to think about dark energy in particular. So it's pushing the galaxies around. Is that the thinking?
Maybe I wouldn't think of it maybe as pushing the galaxies around, but it's essentially creating more space. And then those galaxies are moving into that space as it's creating more space for the galaxies to move into. I love analogies. And so another great analogy that I like to think about is blowing up a balloon. And so if those galaxies were dots on the edge of the balloon, as you blew it up, you're essentially just kind of creating more space. And those galaxies aren't really being pushed away from each other. They're all still on the surface of this balloon, but they're just slowly kind of moving into that space and moving away from each other.
That is a great analogy, actually. It actually really makes it a clearer picture to me. So it's, in a sense, then I guess, is if those galaxies are sort of sitting on the edge of the balloon and the balloon is expanding, does that mean that it's providing some sort of spatial limit or boundary to the galaxies in a way? Like if the galaxies are the physical matter, is this providing some sort of boundary to the physical matter?
Yeah, that might be outside of my expertise
Yeah.
or outside of what exactly we know. But yeah, these are great questions.
And do we know if dark energy works similarly, I guess, to physical energy in the sense that, thinking, for example, of Newton's laws of motion, where for every action there's an equal and opposite reaction. Is there any evidence that dark energy behaves in that same way, or?
So I don't, not that we have observed that we can say concretely yet, but yeah, that's a great question. And some of the theories of what we might find out from what dark energy is might break down our understanding of Newton's laws of physics. Like I said, with that ball, throwing that ball up in the air, we would expect for it to come down like gravity here, but those large scales, the entirety of the universe, we might have something new to learn about gravity or something new to learn about Newton's laws.
That's fascinating to think about. Yeah, very, very interesting. And so I guess, the scientific method involves normally, I think, direct observation, right? So as you said, you're looking indirectly at dark energy by looking at these galaxies and making inferences. And I guess, is there any change to the scientific method in terms of, well, you're not able to observe the thing directly? How does inference work into the scientific method? I guess, is there a potential for error or discovery of new things in the future that would change these inferences?
Yeah, I mean, of course, without direct observation, you can never know 100% for sure. I think in an ideal universe, we would know 100%. I do think, though, that there are, especially with enough observations and enough inferences and enough perspectives and different angles of looking at the same question, you can make a pretty tight argument. If I go to bed at night and then I wake up in the morning and everything is wet and the ground is wet and I have big puddles outside, I'm going to make a pretty strong inference that it rained last night. Of course, there are other things that could have happened, right? But I think it's a pretty safe bet that you can say that it rained last night, or you could, go walk down the street and get another perspective and see if it was wet way down there. And from that angle, your neighbors would say, oh yeah, it rained last night. So in that way, I think that inference and providing that, something that's not even direct observation, we can still have a pretty tight science case around that.
And I guess the more perspectives that are brought into it, such as with citizen scientists, I guess that just helps to add credibility to the evidence, or add some sort of solid basis for the evidence.
Yeah,
Yeah.
exactly.
Yeah, interesting to think about what might be discovered with this. In the scientific community now, is there a sense for what this might lead to in terms of discovering how dark energy works, for example? Is there a sense of what that knowledge might lead to?
Yeah, I mean, there's so many things I think that it would be helpful for within the field of astronomy, especially, teaching us about galaxy evolution, and how galaxies evolved over time, how stars evolve, specifically how our Milky Way galaxy and our solar system came to be, and how dark energy plays a role in that large evolution over time. I think could be really interesting and really valuable.
Yeah, for sure. And that answers that, I guess, age-old question, why are we here? And I guess if it helps us to understand how we got here, then maybe we understand more of why we got here. And yeah, really fascinating to think about what could be out there that we can't see, but we know is out there. And certainly the science and the type of equipment, I guess, now that's available for this is really providing data that didn't exist before, I guess. And so you mentioned the telescope. How does it work? What is it operating on? What kind of light is it looking at? I guess from what spectrum?
Yeah, good question. So yeah, it's the Hobby Everly telescope that is at McDonald Observatory out in the Davis Mountains of West Texas. And it's a really awesome, special place. I have to talk about it because it's one of the largest international dark sky reserves. So, one of the largest protected places on Earth for dark skies and the lowest amount of light pollution, which is really awesome. And so, yeah, the Hobby Everly telescope is one of the largest in the world at 10 meters across. And it is taking spectra of those galaxies, specifically Lyman alpha emitting galaxies. Those are those galaxies that I was talking about that are sitting at about 9 to 11 billion light years away. And Lyman alpha is essentially just a strong, bright emission line from hydrogen that we're seeing from those galaxies at that certain epoch within the universe's history.
So that spectrum wouldn't be naturally visible spectrum, I guess. It's only visible through the equipment of the telescope.
Right, exactly. So we like to talk say something is redshifted. And so it sits at about a redshift of 2 to 3, those galaxies. And so what's happening is that the light is being redshifted to us into the visible so that then we can see it. But it's actually emitted at a different wavelength whenever it leaves those galaxies. Getting into the weeds a little bit, but yeah.
Right. Okay. And red shifting is as the light moves away, it's said to be red, I guess, in terms of, I guess it's not really color, it's just the wavelength.
Yeah, right. So it's being redshifted because of that expansion of the universe. And so things are expanding and moving away from us. And so yeah,
Hmm.
that's where we're.
And is new equipment like the James Webb Space Telescope, is that able to contribute anything to these observations? Because it uses the infrared spectrum, I think, right?
Right. Yeah. So a little bit different than what we're doing. And we won't directly it's not directly a part of our experiment. But all of the knowledge that we're learning from the James Webb Space Telescope can definitely help us in terms of the science case and how we're understanding just the universe and how things evolve over time for sure.
Hmm. It'd be interesting to see how all of that knowledge is brought together. If the Webb telescope is looking at one spectrum, you're looking at another spectrum, and then factor in the time between all of those spectrums. Really interesting, and certainly the Webb is very new in its observations, so we'll see what emerges from that, I guess. Yeah, so it's been great discussing the project, and I'm really interested in following this, and I think our readers would be as well, in terms of what comes out of it, what conclusions can be made from it, and really interested in knowing the experiences of the participants, especially those who spend a lot of time and get really interested in it. It'd be really fascinating to see what comes out of their experience from this. Do you have any other citizen science projects planned after this one, or?
This is the main one for now. We might release some new workflows, so it would still be dark energy explorers, but we might release some new things for our participants to classify. We have one that we maybe want to do, which is around black holes or active galactic nuclei. And so being able to classify those, I think would be really cool. I think the public would hopefully find that super interesting too.
Yeah, that would be. So zooniverse.org, and look for Dark Energy Explorers. Sign up, participate to whatever extent you want. And as you said, you'll send a link when a person creates an account, you'll send a link, and that will give them some more connections in terms of the YouTube channel that you mentioned and other communications.
Yeah, all those links can be found too on the Dark Energy site once you get to the homepage. Yeah, once you sign up, then you're one of our participants and we'll get emails about those events.
Well, that's great. I will do that immediately following this discussion. So yeah, Lindsay, it's been great speaking to you, and we certainly look forward to hearing more, and I look forward to learning from the experience too. So it's been wonderful to connect, and would like to wish you very good luck with your project, and that some interesting new information is found from it.
Awesome. Yeah, thanks so much.
Thank you for talking, and we'll catch up with you soon, I hope.
Sounds great. Yeah, thanks.
Our thanks go to today's guest, and to you for listening to the Quantum Feedback Loop. You can find more information about this discussion in the Quantum Record at www.thequantumrecord.com. Please subscribe to this podcast wherever you get your podcasts, and join us for more fascinating discussions with the people who are pushing the limits of knowledge today for the benefit of tomorrow.